Okay, we're looking at section 6.3, sum and difference identities. And the sum and difference identities can be used to find exact values of trig functions of certain angles. These values are written in non-decimal form using radicals. We can also use the sum and difference identities to simplify expressions. And using the sum and difference identities, we can establish more identities, and you're going to see this in section 6.3, or sorry, section 6.4, the next section. Okay. Having some difficulty when I move this up to show the sum and difference identities, so I'm going to leave it where it is right now, and then hopefully it's going to be okay. But the things I want to point out, there are three different families: the cosine family, the sine family, and the tangent family. And with the cosine family, this is the cosine of alpha plus or minus beta. Now, if you notice, the sign is plus or minus, and that equals cosine alpha, cosine beta, minus plus the sine of alpha, sine of beta. So the functions repeat, which means cosine, cosine, and then sine, sine, but the sign, plus or minus, alternates. So basically what this means is the plus is on the top here, and it matches with the minus on the top here. And then vice versa, if it's a minus, you're going to have a plus. Okay, and then if we look at the sine family, you're going to notice that it's sine alpha plus or minus beta, and then it equals sine alpha cosine beta. So the functions alternate, but the sign repeats. So you'll notice again that this side is plus minus. So a sine sum, you're also going to put a positive in between the alternating functions. And then I'm not going to move this up, but you can see this on your paper. For tangent alpha plus or minus beta, the numerator is the same sign, so it's plus or minus. But in the denominator, you'll see again it's that sign, it's flipped, it's minus plus. So if it's tangent sum, you're going to put a plus in the numerator, a minus in the denominator. Okay, I'm going to move this up, and hopefully you're still going to hear my audio, and then we'll go through some examples. Okay, now this table is from section 5.2, trig functions of special angles. And we have our radian measure angles, and then all the trig functions, what they equal. Let's go ahead and put in the degree measures next to it. So you have 0 degrees. 30 degrees is pi over 6. 45 degrees is pi over 4. 60 degrees is pi over 3. And then 90 degrees is pi over 2. Those are just first quadrant angles. So if you remember our all-star trig class, or all students take calculus, to remember which ones are positive or negative based on the quadrant. We can also, let me get rid of our A here. We can draw in our unit circle. And if you don't have this table, you can still figure out, here's a 45-degree angle, 30-degree angle, and here's a 60. You can still figure out what the sine and cosines are by drawing this little picture. So remember it's x comma y, and the x is the cosine and the y is the sine. So let's put in our angles here. So we have 0 degrees, this is pi over 6, pi over 4, pi over 3, and then 90 degrees is pi over 2. Okay, let's do our cosines first. Cosine starts at 1, and then it's the square root of 3 over 2, square root of 2 over 2, 1/2, 0. And if you notice the pattern in the numerators, It's square root of 3, square root of 2, the square root of 1, which is 1, and then the square root of 0, which is 0. The numerators just kind of decrease. And then we do this in the reverse order. So we're going to start up here at 1. Then we have the square root of 3 over 2, square root of 2 over 2, 1/2, and then 0. And then again, remember you can apply these to any quadrant based on the corresponding reference angle. Okay, so if we look at our first example here, we have the sine of 75 degrees. Well, 75 is not one of our special angles, but it could be the sum or the difference of two special angles. So we're going to set this equal to the sine of two special angles, and I'm going to give you the answer of 30 degrees plus 45 degrees. So in terms of what we've been doing, alpha is 30 degrees and beta is 45 degrees. So if you look up at your sine family and the sum, this is going to be the sine of 30 degrees times the cosine of 45 degrees plus, because we keep the same sign, positive, negative, of the cosine of 30 degrees times the sine of 45 degrees. So 30 and 45 are our special angles. We can find out the sines and cosines of all of those from our table or from our unit circle. So the sine of 30 degrees is 1/2. Cosine of 45 is the square root of 2 over 2. Cosine of 30 degrees is the square root of 3 over 2. And then the sine of 45 is the square root of 2 over 2. Now let's multiply each of those pairs together, so we get the square root of 2 over 4 plus the square root of 6 over 4. Our fractions have a common denominator of 4, so we can add the numerators together, and we get the square root of 2 plus the square root of 6 over 4. Here is our exact value of the sine of 75 degrees in radical form. Now, just a word of caution, the sine of 30 degrees plus 45 degrees does not mean you distribute the sine function. That's not what this equals. So let's just double check that. We just found out what the sine of 30 plus 45 degrees is above. So that's the square root of 2 plus the square root of 6 all over 4. And let's just prove that it's not equal to the sine of 30 plus the sine of 45. Well, the sine of 30 degrees is 1/2. The sine of 45 degrees is the square root of 2 over 2. Again, we have a common denominator, so we add the numerators. That's 1 plus the square root of 2 over 2. And you can see that those two sides are not equal to each other.